Alright, we'll go ahead and get started. Today we'll be exploring SOLIDWORKS Flow Simulation and how best to analyze all-electric designs. My name is Enrique Garcia, and I'm a Senior Applications Engineer here at GoEngineer, specializing in our simulation products. This will be part one of a three-part presentation series that will explore various capabilities of SOLIDWORKS Flow Simulation. Before we jump into the agenda for today, here's a general slide showing how SOLIDWORKS Flow Simulation is offered. One will typically purchase SOLIDWORKS Flow Simulation and specify if you would need any of the below two specialty modules, whether that be the HVAC module or the electronics cooling module. As we go along with our webinar series, there will be some tools that we will be using that are only available in our HVAC or our electronics cooling modules. All right, so here's the agenda or roadmap for our webinar series. We'll start today with our first webinar by setting up our all-electric design with some idealized conditions to get a baseline of where our temperatures and our overall performance of our design will be. Then next week, we'll take that up a notch, and we'll put our design in operation in the hottest place on Earth. Then for our last webinar, we'll keep refining our setup and flow simulation with those hellish conditions and begin to use some of our more specialized tools available in the electronics cooling module and take another look at the accuracy of our design. We'll also introduce some tools that can help with more accurate thermal power output for our analyses. Before I forget, just as a side note, in case something comes up, or if you have to leave this session early, we'll be recording this webinar and we'll post it onto our GoEngineer YouTube channel after a few days. Also, if you have any questions while I'm presenting, feel free to ask, and if all goes well technically here on my end, I'll be able to see your questions and answer them as I go along. I'll also have some dedicated time at the end of the presentation for questions. So let's intro a bit and quickly comment on the status of current designs. So in many industries, we're at a transition point from the oil and gas age over to a new all-electric era. And so as more of our enterprises continue to work at reducing our carbon footprint, many of us are looking to an all-electric solution for our designs. As we continue to miniaturize our knowledge from our past designs and begin to rely on different tech such as integrated circuits and more compact components, it becomes paramount to efficiently and reliably predict and control the thermal heat energy generated by these systems, especially if they'll operate in extreme environments. This brings us to the need for the use of simulation software such as SOLIDWORKS Flow Simulation. Before we go on over to my software screen, I want to just point out that as a main focus of this example, we'll be looking at two integrated circuits, just under these two heat sinks right over here. All electronic components have an operational temperature limit that we have to respect. We'll say that for us, we want to ensure that our two ICs won't go over 95 degrees Celsius, which is roughly about 200 degrees Fahrenheit. If we do, there's going to be a reasonable risk of component failure. Let's go on over to my active session of SOLIDWORKS and walk through an initial setup of a simple electronics box and show how we can get some initial results for an all-electric design in just a few minutes. All right, now with Flow Simulation add-in turned on and my model open, I want to navigate over to my Flow Simulation tab in the Command Manager and start a new project. We're going to be using the wizard for this. Let's give our project a name here. We'll call this one Standard Conditions. And this is going to be our baseline set of results here, or setup moving forward. Let's now focus on our units. For our units, let's go ahead and change the temperature from Kelvin to Celsius. Let's continue along with the wizard. And again, this is a preliminary kind of setup only. So we're going to start simple. And we do that by changing our analysis type here to an internal analysis to focus on what's going on inside of the box to start. Let's turn on conduction. And let's turn on gravity. And let's change our acceleration due to gravity to a different direction vector here. And we can confirm the direction with the arrow there in the graphics area. Let's select a default fluid medium here. So we're going to go under gases and we'll add air as the default fluid medium. And now let's go in and select the default material, which again, we're simplifying. So we're going to be choosing this default insulator. We are going to be overriding the materials here in the next step. So we'll continue on for now. For wall conditions, we'll just leave the default wall conditions. And for our initial conditions, we're going to leave the default temperature and pressure, which is room temperature for our temperature and our default pressure. Let's click Finish to create our initial project here. You'll notice above the SOLIDWORKS design tree, we have a new tab called Flow Simulation Analysis. This will give us access to our project manager, and down below we have access to our flow simulation design tree. With our flow simulation design tree, we can easily add different constraints and boundary conditions to our project. Let's start by adding and assigning materials and material properties to all our individual components. We can do this both by importing data from our CAD model or from going in fresh and assigning individual material properties to each individual component. Let's start by adding some stainless steel to some of our plates for our electronics box. And let's switch on over to copper. And let's assign copper to our two giant transformer components. Next, under silicon or semiconductors, let's choose silicon. And we'll assign this material property to our 6 PCUs here on the board. Or excuse me, our PSUs here, and to our 6 round smaller capacitors. And lastly, well, let's select the components that make up the 2 ICs below the heat sinks. Next, let's assign aluminum, and we'll assign them to the 2 heat sinks above the ICs, the very large capacitor, and the 4 medium cylindrical capacitors here. Lastly, let's assign a FR4 4-layer PCB material to the PCB or the printed circuit board component. Now, because of the material properties of the PCB, we have to pick and specify a direction of non-isotropy for the material conduction. For us, that's going to be aligned with the Y direction. Let's accept it, and let's close the property manager, and we're done with the components for now. Next, let's assign some boundary conditions to the environment. Let's go in and assign an environment pressure so we can have some openings to the environment. We'll be going and doing that here next. Let's choose these semi-transparent lids. All right, so that's how we're going to be introducing our fluid medium through these vents here, and it's going to travel through the components, across the heat sinks, and out of the fan. So let's accept this boundary condition, and now let's assign a fan definition so we can have an outlet fan here. We're going to be choosing an external outlet fan, and for the reference face, we're just choosing here this face of this lid as a reference. Now this is idealizing the actual fan. We're going to have a fan curve that's built in. So if you have a white sheet for your fan, you can enter that in our database. And you can make your own custom materials for that, or custom fan database entry for that. Here I've done that under user defined, under custom PAPS DC axial fans, and there's my fan. Now, if you want to do this on your own end, you can go in and go to the database we have called the engineering database, where we catalog and save and store all of this information. So here's my entry for my custom fan. I have some item properties I can enter from the white sheet, and very importantly, we have our curve here, our fan curve. So once I've entered and specified the actual fan, and I've specified that this is going to be pulling air fluid medium out of the system, I'm going to click OK to accept the fan. There's my symbols indicating the direction. And that'll take care of my fluid medium and fluid flow. Now let's focus on heat transfer. We're going to do this by assigning some heat volume sources or some volume heat sources to the individual component or major key players in the system. I'm going to start by putting in a 2.5 watt heat source on the two integrated circuits that make up our little CPUs here under the heat sinks. So I'll start by doing that geometry as 1, and I'll choose the other geometry for the second IC. Next, let's assign a volume heat source for the 4 medium capacitors. Those will have a combined output wattage of 5 watts, and let's go ahead and choose those components next. Next, let's focus on that large capacitor that will have an output of 10 watts for the large capacitor. And now for the two large transformers, that will have a total of 4 watt output, power output for these two large transformers. Notice that you can enter additional information if you don't know the wattage. If you know maybe the temperature, you can add the temperature, or if you want to do a heat generation rate, you can do watts per meter cubed. So whatever data you have some options for choosing how to input the heat energy into the system. Let's add our last volume heat source and close the property manager. Now, we mentioned that one of the main goals for this system and setting up the system is to keep track of the temperatures of our two ICs under the heat sinks. We're going to do that by formally asking the software to do this by means of an engineering goal. This will ensure that we have appropriate convergence of the solution in those areas when we run the calculation. So in my SOLIDWORKS Flow Simulation property manager or design tree here, I'm going to right click under goals and I'm going to go in and choose volume goals so we can keep track of both volumes separately. I'm going to go and focus in and choose these two components as my first volume goal. And I'm going to come down and find my temperature of the solid parameter. And I'll make sure I choose the maximum. So let's add that as our first goal. And let's do the same thing on the other instance with the other IC. This will give us two individual volume goals, maximum temperature volume goal that we can keep track of. Now at this point, we can run the analysis. Now, since running an analysis for flow simulation can take some time, I have pre-set up and run this same project here under the project manager. Let me go ahead and activate that, and let's run through and interrogate some results. Now, once you've run your project, you'll have a results folder where you can go in and interrogate your results both qualitatively and quantitatively. Some of the more popular qualitative plots are going to be your cut plots. A cut plot can cross-section your results, and you can either, let me show here, let me do one from scratch actually. I can do a right-click and select Insert, and I can select a reference for how I want to section my results. I can click on the preview, the detailed preview icon to get a preliminary kind of result here, and I can continue to adjust my options. So I can continue to increase maybe the quality of the result here. I can maybe bump up the number of colors there to give us a more smooth gradient for our temperature of the fluid. Maybe I want to look at the temperature of the solid instead. I can choose that. Or if I want to choose both the temperatures for the fluid and the solid, I can do that as well. Once I'm done, I can click OK, and I can have my preview there kind of set. And I've made a couple of other plots as well that we can keep track of. Here's a second one, and here's my original, which was in the same position. Now, when I have all of these cut plots shown, I can go in and I can animate those plots as well, and it'll cut through the whole section of the model and show you results throughout the whole computational domain or the calculated volume of this here project. Let me stop the animation. I can go in and I can add additional types of plots. Let me hide these plots here for a moment. And let's show a surface plot. With surface plot, I can go in and I can color code all surfaces of interest. For example, here I've selected the surfaces of the heat sinks, the ICs, and the PCB to show results for. When you're looking at these results, we have the color bar, which can kind of help you gauge what the temperatures could be of those heat sinks or the ICs. So in addition, with these qualitative plots, I can turn on something called the probe tool to go in and display or call out the results in specific areas of interest. To do this, I'm going to right-click on the results folder and choose probe. Once the tool is on, I can hover over any turned on or shown result plot and click in an area of interest to get information from them. In this case, I can see I'm about 60 and 69 degrees Celsius for the two ICs. I can right-click once again on the results folder to turn off the probe functionality, and I can also manage the actual probe display results as well. I can display or I can hide those probe display results. So moving on, let's talk about flow trajectories. So flow trajectories allows us to help visualize the fluid flow or the fluid air medium around the inside of this electronics box. To access that, we can right-click under flow trajectories and we can create a new flow trajectory. I'm just going to edit this one to show you what I did to set this up. So a good practice of mine when you're adding flow trajectories is to choose the inlet faces and the outlet faces of the project. So in this case, we have those three faces selected, and then we can tell it how many of these injection points I want to add to the model. The more injection points or number of points, the more detail I can go in and visualize with in the volume that we're trying to visualize. Under appearance, we get to specify the type of geometry that we want to use. We can use things like arrows or spheres, lines, pipes to be able to characterize your flow fields. And we can click the detailed preview icon to see what it'll look like before confirming these results. So in this case, the size looks fine here. And under the color by, I can see which component I want to be able to visualize. In this case, the temperature of the fluid is what we're characterizing with these flow fields. I'll click OK to accept flow trajectory settings set. And at that point, I can right-click and I can animate the flow trajectory field. Let's stop that and let's talk about some of the other type of quantitative results we can get with flow simulation. Let me hide my flow trajectories next. And let's talk about surface parameters. So we have a section down below that's called surface parameters, volume parameters. And this allows you to select either surfaces or volumes to call out results that were calculated from the whole computational domain. In this case, I can make one here from scratch, a surface. I can select Insert Surface Parameter. I can have anything pre-selected to add it to the selection set box, or I can go in and freshly clear and select another surface, and then tell it what I want to harvest from my result set for that surface under Parameters. In this case, I want to select the temperature of the solid and click Show. And this will give me some information of the temperature of that heatsink. Same thing can be done with my integrated circuit or any other component, anything within the computational domain of the project. So that's surface parameters. In a similar fashion, I can do the same with volume parameters. With volume parameters, I can select Insert. I can choose a component, maybe this particular small capacitor, select temperature of the solid, and harvest the results there for that whole volume of the model. Once again, we have our minimum, we have our maximum temperature there, which is about 30 degrees Celsius for this particular component. Now I can do the same with my very important ICs, or two integrated circuits under the heat sinks. However, because we've selected to go in and converge those specific areas and get some official results under engineering goals. Right down here, I can go to the results folder and I can go in and select goal plots. So I can do one fresh here for you here. Well, in the presentation, I can select insert and I can tell it to call out the two geometries that make up each IC to show what those official results were. So again, we've chosen these and we've made specific engineering goals so that our solver can make sure that we're converging results for these specific areas of interest, because they are paramount for what we're trying to find out. If I had other components that I needed to do so, I would need to also make engineering goals for those components so that I can ensure that my results are converged in those areas. Right now, every other component besides these two are sort of preliminary as far as convergence of the result. So looking at our results here, we can see that both ICs have a maximum temperature of about 69 or 70 degrees Celsius, and then the other is about 62 degrees Celsius. So we can come to the conclusion that the operating temperatures of these ICs are well below the operational limit of that 95 degrees Celsius that we set for ourselves earlier in the presentation. Let's go on back to our presentation screen and finish up some slides. All right, so that sums up our first setup for this presentation. Next week, we'll explore how our all-electric design will perform when left outside in direct sunlight on the hottest place on Earth. Before we end with any questions, I just wanted to promote our dedicated GoEngineer YouTube channel. We post videos here very regularly and invite you to subscribe and stay up to date with our latest uploads. We have a wide range of topics that are covered, including simulation. So definitely feel free to stop in and check out what we have. We also produce a blog on our website that's very active, with many tips and articles with useful information regarding SOLIDWORKS, simulation, and many other technical topics, as well as fun projects our engineers have been doing with 3D printing and scanning. All right, with that being said, I'll stay on for a few minutes here to help answer any questions you may have. But thank you for attending my presentation here today, and we'll see you on the next one.